With that, please help me welcome our speaker for the morning, astrophysicist, Dr. Jessie Christiansen, project scientist for NASA's Exoplanet Archive and research scientist at NASA's Exoplanet Science Institute, where she searches for, characterizes, and catalogs planets orbiting other stars. In 2002, Jessie Christiansen earned a Bachelor of Science, Advanced Studies in Physics and Mathematics at Griffith University in Brisbane, Australia. She then continued her studies to receive a Bachelor of Science First Class with honors in astronomy at the Australian National University, Canberra. She completed her PhD in astronomy at the University of New South Wales, Sydney in 2007. Dr. Jessie Christiansen, welcome to the Greenway Talks online at Palomar Observatory. Thank you for taking time to speak with us today. And we'll take questions at the end of the presentation. And for that reason, right now, I'll ask everybody to turn off their microphones. And with that, Dr. Christiansen, we're ready to tour the Hooniverse.
Great. Thank you so much for having me. I wish I could be there in person. The pandemic's been really hard on everyone. And, as an observer who loves coming to Palomar, having to observe remotely, it's fantastic that we were able to get the data, but it's not the same as being there and getting to see everybody and getting to play with the big telescopes. And so one day I'll be back up there, but in the meantime, it's a pleasure to see you all online. Today I wanted to talk about exoplanets in science fiction and how what we've really found in real life has been even more wild and wonderful than we could have imagined. So let me get my presentation up. I remember to check all of those boxes again. Great. And I'll start that and I will confirm that you can see the slide, not the presenter mode. Great. Okay. So let's talk about exoplanets in science fiction. If we were there in person, I'd ask for a show of hands who recognizes this fictional world. I'll give you a second. Maybe this will help. It's the Enterprise. This is Vulcan. This is Spock's homeworld from the Star Trek universe. It's called Vulcan, also known in the extended Star Trek universe as Vulcan, Vulcanus A2, Navasa 2, or 40 Eridani A. And I'm going to move my little Zoom floating head because I'm in the way. There we go. Okay. So yes, stars in the sky, in the real sky, have lots of names. And in science fiction have lots of names as well. So this planet has many names. Okay. So let's keep going. So we've only found exoplanets really in earnest in the last 25 years or so, but we've been thinking about exoplanets, so planets around other stars, for thousands of years, actually. So in 600 BC, 2,500 years ago, the Greek philosophers were talking about this idea of other Earths. Was Earth singular or plural? And they were thinking about it in a purely hypothetical way, kind of the way we talk about multiverses today. Like, this is a really neat idea. We have no idea how we test it yet, but let's think about it because it's a lot of fun. Plato and Aristotle actually argued that the Earth was unique, that there weren't other Earths. Now, again, this was a thought experiment. So who knows 2,500 years later whether they were talking about literal other Earths or multiverse Earths or multi-parallel Earths, but they argued that there was only one Earth. In science fiction, the first time we really start to see, our imagination leave the surface of the planet and go somewhere else physical is Dante's Paradise. About 1300 AD, he tells a story based on concentric spheres around the Earth. And this was, before the Copernican revolution. So they thought Earth was at the center and that the planets were in spheres, concentric spheres around the Earth. So he tells the story, Dante's Paradise, which has these other worlds in it that have stories set. So this is one of the first times we really see in fiction these representations of stories off-world, somewhere else. Okay, back to the science side. In 1592, so now we're in the Renaissance. So this is a really incredible time for art and math and literature and science in the Western world. And you have this Italian mathematician, Giordano Bruno. And this is a quote that I'll read. There are countless suns and countless Earths, all rotating around their suns in exactly the same way as the 7 planets of our system. And I'll leave it as an exercise for the reader in 1592, which were the 7 planets he was referring to. So Giordano Bruno was actually burned at the stake for saying this. He actually also said a whole bunch of silly stuff about the Catholic Church at a time when it was very dangerous to say a bunch of silly stuff about the Catholic Church. But one of the reasons he was executed was for claiming the plurality of worlds, for saying that there were other planets, which was against the Roman Catholic doctrine at the time. But he was one of these first people, the first scientists to really articulate this idea that, that the solar system wasn't unique in some special way, that the stars in the sky could have planets around them just as well as our sun had planets around it. All right, back to the science fiction side. In the 1700s, we really see the moon, our moon, start to be a setting for many works of literature. So there's a bunch of stories that get set on the moon. In the 1800s, the focus really moves to Mars. And this is because, people have seen the canals on Mars, the lines that looked surprisingly straight and long to be natural features. So people were thinking about Martians. So in the 1800s, you really start to see a lot of stories set on Mars. Back to the science side. Telescopes were invented, are improving. We're starting to really look for planets around other stars. We've had this idea now for hundreds of years that there are planets around other stars, but it takes a long time for the technology to catch up. So in 1952, so 70 years ago, astronomer Otto Struve suggests a technique to observe planets around other stars. And basically the technique is this. They already knew about 2 stars orbiting each other, binary stars, because if you measure the spectrum of a star, if you take the light, split it up into a spectrum, you can see from the velocity shift that sometimes the star is moving towards you and sometimes it's moving away. And so if you see 2 stars and they're doing this, you know that they're going around each other. And so Otto Struve was like, okay, what if we took out one of those stars and put a planet in instead, a giant planet that was very close to the star? That would actually induce a large enough wobble on that primary star that we could observe it if we looked at the star's spectrum. And this is called the radial velocity technique. And at the time, so this is 70 years ago, at the time, everybody thought that this idea was a bit crazy because we only had our solar system. So our solar system has a sun, a bunch of rocky planets, then a bunch of giant planets far away. So people were like, well, how would you get a giant planet super close to the star? How would that form? How would it stay there? So basically between 1952 and 1995, this paper has less than 10 citations, like 7 or 9 citations. Hardly anybody thought this was a good idea. But so this idea was out there, how you could do it if they existed. Okay, on the sci-fi side, we continue to see this evolution of stories off-world, and now we're moving to film and TV. So in 1951, we have the movie When Worlds Collide, and in 1956, the movie Forbidden Planet. And so these are, some of the first times we really have movies set on what are essentially fictional exoplanets, so fictional planets around other stars. In 1963, we see our first exoplanets on TV, which is in Doctor Who, and there'll be more Doctor Who later in the talk. And I have a TARDIS behind me, as already been noted by someone in the audience. So yeah, so first time we see exoplanets on TV. So you can really see this evolution in storytelling off-world. And then finally, in 1995, our technology we've got great telescopes, we've got CCDs, we've got fantastic spectrographs. Finally, we're looking at a star and we see it wobble in exactly the way that Otto Struve proposed, 50 years earlier. So we find our very first planet orbiting a normal sun-like star using the radial velocity method in 1995. And just, I think 2 years ago now, that was awarded the Nobel Prize, that discovery of a planet. Not to Otto Struve, who proposed it, but to the scientists who actually were able to measure the wobble. So that's very exciting. Now, after thousands of years, 2,500 years from this idea, are there other Earths, to the development and execution of the technology, we know it's true. We know that there are planets around other stars. So that is pretty cool. Okay, so this is the NASA Exoplanet Archive. And as Stephen mentioned, that's where I work. I'm the lead scientist at NASA's Exoplanet Archive. So one of the things I do is I put planets in this archive every week. I have a team of scientists and data analysts that I work with. Now, what this is an overview page for a given planet that we were putting in a few years ago. Now, remember I said stars have lots of names. So this is the aliases for this star, and you can see all of the different names that this star has. So I'm sitting there and I'm typing them all in. And one of them jumps out at me. It's 40 Eridani. And I'm like, 40 Eridani? Why do I recognize that name? And I'm thinking about like all of the outreach I've done and stories I've told about the sky and thinking about the constellations. And I'm like, I don't remember anything special about 40 Eridani. Why do I know that? Now, I'd love to say that I just was able to pull this fact out, but in fact, I had to Google it. 40 Eridani is Vulcan. So at the start, I remember I showed you this is Vulcan, and one of the names for Vulcan is 40 Eridani A2 because it's the planet that orbits the star 40 Eridani. So in real life, 40 Eridani is a triple star system. So here's 40 Eridani A, and then nearby there's a binary system B and C. So in the Star Trek universe, 40 Eridani A, this star here, is the host star of Vulcan, of the planet that orbits the star that Spock is from. So it turns out that's why I knew 40 Eridani from Star Trek. So is the planet Vulcan-like that we found, 40 Eridani A, B? It is not. What we found was a giant planet. And a lot of what we've found so far are giant planets because they're easier to find. So for instance, this method that Otto Struve proposed that relies on the wobble, the smaller the planet gets, the smaller that wobble gets. And so your telescope has to get bigger, your spectrograph has to get more precise to measure really what we're looking for. If you're looking for an Earth-like planet, the star is moving by centimeters per second, like slower than a turtle walking on the ground. So we're looking, thousands of light years away at a star just trying to wobble very slightly. So we found the star that Vulcan orbits, but we haven't found Vulcan yet. Okay, this is Kepler 62F, an artist's impression. Every time I talk about a real planet in this talk and show you a picture, it's always an artist's impression. This is Kepler 62F, which is the actual planet that is most like Vulcan that we found, in the fact that we think it's a rocky planet that's around a star like 40 Eridani. So this is the closest we have so far. Okay, but this was a really fun revelation for me, right? That, the planets in the Star Trek universe, the people who wrote Star Trek knew about real stars in the sky. And they, used some of those names. So I did this exercise. So I went through the online Star Trek Memory Alpha Wiki, which is a very extensively fan-kept database of everything in the Star Trek world. And I went through. There are 930 named planets in the Star Trek universe up until Discovery. So this isn't including Picard or Lower Decks. So 938 planets. 51 of those, I went through each one, 51 of those were claimed to orbit stars where I could map those to a real star name in the real world. So you can tell most of them were just completely fictional, but some of them, they really used real star names. So 51 of them were stars that I could recognize. Sometimes I had to do a bit of imagination, like, a planet orbited Taurus Alpha, and I'm like, well, that could be Alpha Taurus, so I'll give that. But mostly just real stars. Of those 51 real stars, 7 of them, I went to the Exoplanet Archive and cross-checked, 7 of them have real planets around them. In the real world, we've found that they have exoplanets around them now, including 40 Eridani A. So there's one system in particular I want to talk about called Tau Ceti. So this is an artist's impression of Tau Ceti. It's a 4-planet system. You can see 1, 2, 3, 4 orbiting this star. So Tau Ceti, it's got a common name, so it's, pretty bright. So this is the constellation Cetus, and so Tau is this one here. So it's actually a naked eye star. You can go out and find Cetus and find Tau Ceti. It's got 4 planets around it. The reason it's cool is because in the Star Trek universe, Tau Ceti in the Star Trek universe has 4 planets around it, and the real Tau Ceti has at least 4 planets around it. So not only did they pick the star, but they actually picked the number of planets as well. Now, in real life, we're pretty excited about the planets around Tau Ceti. Let me explain a little bit why. So these are 2 graphics showing the Tau Ceti system. So here's the star, and here's the planets G, H, E, and F. I'm going to pause to apologize for exoplanet names because they're all garbage. I'm very sorry. I don't get to name them, but they've all got rubbish names. All right, so Tau Ceti, G, H, E, and F. And then here's a schematic around our sun. Now, the planets are to scale with each other, but they're not to scale with the distance to the star. So the planets have been made much, much bigger so you can see them. So this is the sun. So this green shaded region here is what we call the habitable zone. So the habitable zone is the distance away from a star that a planet could be, where if it had a rocky surface and an atmosphere like Earth, water could be liquid on the surface. It's basically a temperature. There's a certain temperature range where for a given atmosphere, water could be liquid on the surface. And that's the shaded region here. Now, one of the reasons we're excited about Tau Ceti is because it's got 2 planets that are right on the edge of the habitable zone. Now, they're a bit big, so the planets are relative to each other in scale. So they're a bit big. They're 1.5 to 2 times the size of the Earth, which makes us worry a little bit that the atmosphere will be much thicker and have much higher pressure, which would be bad. And they're right on the edges of the habitable zone. So it's easy to imagine that they're actually not particularly habitable. Like E is probably too hot and F is probably too cold. But, we don't know much about the conditions in the universe that life could exist in. We only have an example of one. So we're kind of constrained to looking for things that look like Earth. So when we're looking at Tau Ceti, the answer is, it could be life, it could be habitable, but it wouldn't be the same as our life. So we're following up on those planets some more to see if we see any evidence that there is life there. Okay, so that's Star Trek for now. We'll come back to Star Trek later. Let's move to a different franchise, a different science fictional franchise. I'm going to bounce around a bunch in this talk and talk about the planets of the Whoniverse. So if we have any Doctor Who fans here, you might have already recognized that this landscape here in the bottom of my slides is actually a planet from Doctor Who called Midnight, which we'll come back to. Okay, so if you had a box that could take you anywhere in time and space, where would you go? So my colleague, JJ Eldridge, went through and made a histogram basically of everywhere that Doctor Who went in the 58 years that Doctor Who has been on the air. So this is a pie chart, a breakdown of all of the places Doctor Who has been. So if you had a box that could go anywhere in time and space, where would you go? Doctor Who spends most of their time on Earth, partly because of BBC budget reasons, partly because of good storytelling, but most of the time we're on Earth. But where else does Doctor Who go? The next big wedge of the pie is Earthlike. Now, what that means is it basically looks like Earth. There's a blue sky and green plants and brown dirt, but it's just called something else, right? These are the Earth twins of the Whoniverse. So planets that are essentially Earth-like, breathable air, plants, life, rocks, oceans, you name it. Very, very, very much like Earth. Again, probably budget reasons. Okay, so then we get to some of the time, a goodly fraction of the time, 1 out of every 8 episodes or so, Doctor Who goes somewhere Earth-ish. Now this is like, there's a purple sky instead of a blue sky, or blue plants instead of green plants, or it's in a cave, the surface is uninhabitable, so you're in caves under the surface. It's in some way a rocky planet that has some, aspects of it that are breathable and livable, but to that other than that, not really Earth-like. Okay. Then sometimes the planets are truly uninhabitable, and that's when the Doctor's in a big spacesuit in a space station on the surface of a planet, and the TARDIS is variously extending or not its bubble of protection. How far can you get out of the TARDIS before you can't breathe? So sometimes the writers genuinely use some imagination and we're uninhabitable. A lot of the episodes are just set in space. So the whole episode is on a spaceship out in the middle of nowhere. And then there's a few where they're truly very different places, like we're at a black hole, or we're at a disintegrating planet, or we're in an asteroid belt, or something like that. Now, the point of this pie chart is to kind of, I'm saying we're reflecting science and science fiction. How imaginative have we been in our imaginings of other planets versus what we found? So you can see in the Whoniverse, which has gone for 58 years and has visited hundreds and thousands of places, that, fully 80% of the time, you're basically on an Earth-like planet. That's not what we've found so far. So when we go out and, look with, the NASA missions that I've worked on, Kepler and TESS and Spitzer, and the ground-based instruments like Keck and Palomar, mostly what we're finding is planets that are bigger than Earth. It seems like the most common kind of planet in the galaxy is something we call a super Earth or a sub-Neptune. So bigger than Earth, but smaller than Neptune. So in our solar system, Neptune is 4 times the size of Earth. So we don't have anything in that size range. We go from a rocky planet to an ice giant and nothing in between. So really interestingly, the universe just invented this whole new kind of planet in between. And we're still trying to work out what those are. We're still trying to work out if they're big rocks, if you just take Earth and scale it up, if they're little ice giants, if you just take Neptune and scale it down, or if they're a genuinely different kind of composition, bulk composition that we don't have represented in our solar system. And examples include something like a water world, right? Like some of these planets we found have densities very similar to just liquid water. And what does that mean? Like, are they deep ocean worlds? What does that look like? So the most common kind of planet we have found is not like Earth, which is at odds with the ability of Doctor Who science fiction writers to come up with a crazy new idea every week. Mostly they're just going to be Earth-like or straight up Earth. And again, this is data that was compiled by my colleague, JJ Eldridge. Okay, so I said I would come back to Midnight. So in Doctor Who, Midnight is a planet that's crystalline, and there's this, ionizing radiation that means that the surface is uninhabitable. So it's a very cool episode of Doctor Who. It's called Midnight. It's basically a bottle episode. Doctor Who and a bunch of people get trapped in a shuttle, and it's very, very cool. It's a very good episode. But the point is they can't leave the shuttle because that radiation outside is too high. And then there's this crystalline planet. So what I wanted to show here was 55 Cancri E. So 55 Cancri is a star in constellation Cancer, and the planet E is the 4th planet out from this planet, the 4th planet that was found in the system. So it's a rocky planet, very, very, very close to the surface of this star. So the orbital period is, around a day. It's 1 day to go around the star. It's only a few stellar radii above the surface of the star. So A, getting a lot of radiation. But B, the rock inside is a very high carbon to oxygen ratio silicate inside. And what happens to carbon when you heat it up and you squeeze it? This planet is being super duper squeezed by the tidal forces from this star, kind of like Io around Jupiter. So if you take something that's very carbon rich and squeeze it and heat it up, you make diamond. So there were cool headlines all over the world when we found this planet because, it was touted as like the diamond planet, like Tiffany's Eat Your Heart Out, biggest diamond in the galaxy found. We don't actually know a lot about the phase state that this would be at given the temperatures and pressures, but we know that what happens to carbon when you heat it up and put it under pressure is it turns into diamond. So there's some kind of crystalline structure making up a large fraction of this planet's mantle. And that's what this diagram is kind of showing, this like sparkly diamond crust around this planet. So this is 55 Cancri E, which is the closest thing we found to something like Midnight, which is this crystalline planet with heaps of radiation where you couldn't be on the surface. You definitely couldn't be on the surface of 55 Cancri E. All right, one more planet from the Whoniverse that I wanted to talk about because it's kind of important is Gallifrey. Gallifrey is described as a red planet with like an orangish reddish sky. But the interesting thing about Gallifrey is that it's orbiting 2 stars. It's got these 2 stars up here. It's orbiting a binary star system and it has 2 moons. So we haven't as yet found any exomoons. So moons around planets around other stars. We're still kind of at the detection limit of finding planets. And now imagine like the extra order of magnitude of sensitivity we need to get moons around those planets. So people have done searches and we could put limits on how common very large planets are. But so far, we haven't found any true, confirmed, robust, we believe it, moons around planets around other stars. But we have found planets around binary stars, and I'll come back to that a bit later. This is just an artist's impression of Kepler 47, which is another system that we found with Kepler. So it's got 2 stars, big star, little star, and 3 planets. So it doesn't have a moon, it doesn't have a planet with 2 moons like Gallifrey, but it does have 3 planets. So this is as close to Gallifrey as I can get with the current holdings of the NASA Exoplanet Archive, Kepler 47. Okay, I've mentioned Kepler a few times now, so let me just stop for a second and talk about the NASA Kepler mission. So it was launched in 2009 and operated until 2018. It was a 1 meter telescope in space. So this whole thing here was about the size of a van, a school van. And it was in a heliocentric orbit around the Earth. So as the Earth, a heliocentric orbit about the sun. So as the Earth goes around the sun, Kepler was basically following behind it like a puppy dog, just following the Earth around the sun. What we did was stare at one patch of sky for 4 years, the first 4 years of the mission, and that's around the constellation Cygnus, basically near Vega. So when you go outside, you can find Vega. You're basically looking at the Kepler field. The goal of the Kepler mission, I'll just replay the animation while I'm talking. The goal of the Kepler mission was to answer the question, how common are planets like the Earth? So Earth-like planets, so rocky planets that are in the habitable zones of stars like the sun. How common are they? Are they everywhere? Are they rare? Is Earth the only one? PowerPoint just restarted. I'll restart PowerPoint. So we launched this mission that looked at one patch of sky for 4 years. I need to rescue PowerPoint, sorry. Gotta reopen it. And what we did was stare at 200,000 stars over and over again for every 30 minutes for 4 years. And we waited for something called transits. I'll just start on the next slide because if that video crashed it, I don't want to crash it again. Look at me being all like, I'll just play this video again. It'll be great. No, crashed it. Okay. Okay, so hopefully you can see the slide. Someone speak up if you can't see. So what we did with Kepler was not the radial velocity method that I've described before. Kepler uses the transit method. Now, the transit method relies on the fact that some of the planets around some of the stars in the sky are lined up just right. So that if you're measuring the brightness of that star over and over and over again, very occasionally the planet will come between you and eclipse some of the light. So similar to solar eclipses and lunar eclipses here, if everything's lined up just right, you'll see a change in the brightness of the star as it's getting eclipsed by the planet. So this is what we did. We looked at 200,000 stars and just waited for these eclipses. So how did we do? We did not find any truly Earth-like planets around truly sun-like stars. But we don't think that's because they're rare. It turns out that the telescope wasn't quite as sensitive as we needed it to be for various reasons. And we just weren't able to get the detection sensitivity to Earth-like planets that we needed. But we found a lot of planets that were a bit bigger, and we found a lot of planets that were a bit closer to the star, both of which we were more sensitive to. And if you extrapolate, which is always dangerous, but if you extrapolate from the shorter period planets and the larger planets into the parameter space of an Earth-like planet around a star in a habitable zone, we think that Earth-like planets are actually pretty common. Something between 20 to 50% of stars like the sun, we believe, have a rocky planet like Earth in the habitable zone, which is pretty wild when you think about it, because the galaxy's got 100 billion stars, and we think that maybe 10, 15% of those are sun-like stars. So that's 10 billion planets. So if 20 to 50% of those have Earth-like planets, that's 2 to 5 billion Earth-like planets just in our galaxy. So that's pretty exciting. I wanted to highlight some of the very cool planets that we found on our way to trying to find Earth-like planets around sun-like stars in the habitable zone. So on this slide, pay attention for 2 sentences. On this slide, the stars are to scale with each other in terms of size and color, and the planets are to scale with each other in terms of size and roughly color. We can guess from their temperature, but the planets and the stars aren't to scale with each other. This is how we showed the graphic. I just have to explain it every time. So this is what we're looking for. Oh, poo. I'm sorry. Why does it keep crashing? Let me get that up again. I don't know why it suddenly started doing that. I'm so sorry. All right. So we're looking for an Earth-like planet around a star like the sun. And that one didn't have any video on it, so I don't know what it's complaining about. All right, let me share again. Okay. So we're looking for the Earth around the sun. One of the first things we found was a rocky planet the size of Earth around a cooler star. And you can see from the temperature on this rocky planet, it's very close to its star. So this was proof of concept we could find an Earth-sized planet, but this was way too hot. This had a very short orbital period, was very close to its star. Kepler 22b was the right temperature, so it was the right distance from its star for liquid water, but it was too big. It was more than twice the size of Earth, and at which point we definitely think it's more like a water world or a mini ice giant than a rocky planet. Kepler 186f was the right size and the right temperature, but orbiting the wrong kind of star. So this is an M dwarf. We'll come back to that in a minute. And then Kepler 452b. Kepler 452b remains the closest thing we think we found to an Earth-like planet around a sun-like star. So let's get to that. So this is Kepler 10c. This is a lava world that we found. So it's a rocky planet, very close to its star, very hot. The closest equivalent I could find in sci-fi is Mustafar, where Anakin and Obi-Wan have their big, climactic battle. I have the high ground. You hopefully remember that one. So this is, Mustafar is the sort of world where this could happen. This is Kepler 22b again, this big potential water world. So similar perhaps to Kevin Costner's water world. In fact, the very first potential water world we found, GJ 1214b, we actually nicknamed it Kevin after Kevin Costner in Waterworld. All right, this is Kepler 186f. That's that planet that's orbiting the wrong kind of star. So let's talk about M dwarfs for a minute. So our sun is a G star, just a boring middle-aged yellow G star. Most of the stars in the galaxy are actually M dwarfs, which are much smaller, less than half the size, and much cooler. So, 3,000 Kelvin instead of 5,000 Kelvin. And that means planets can actually be much closer before they get too hot to be habitable. So Kepler 186f is a rocky planet in the habitable zone of an M dwarf. The reason that we're not super excited about that the way we would be if it was a sun-like star is that M dwarfs put out very different radiation to our sun. So M dwarfs put out a lot of high energy radiation like X-rays and UV, which is, bad for life on Earth. We don't like lots of X-rays and lots of UV. And M dwarfs also have a lot of flares. So our sun occasionally just, burps and does a coronal mass ejection. A whole bunch of stuff comes out. It's not great. M dwarfs do that all the time, huge, very regularly. So it could be the case that any rocks around M dwarfs are just sterilized by this high energy radiation and all of these, coronal mass ejections from these stars. In terms of fiction, who came from a rocky planet around an M star with very different radiation? Superman. So this is like Krypton. This is like Superman's home world. I asked Stephen to canvas you guys for favorite planets, and Krypton came up, so I made sure that was in here. So the whole story of Superman, right, is he was born on a rocky planet around an M dwarf, and when he came to our solar system with the yellow light of the sun gave him powers because the radiation was so different. So that's the sort of thing that would happen here. So we don't know whether life on Kepler 186f would be sterilized or have superpowers. It's one of the two. And then finally, Kepler 452b, I want to talk about for another minute or so. So it's in the habitable zone, so check. Of a sun-like star, check. It's maybe a bit too big. It's about 1.5 times the size of the Earth, which is kind of where we start to think it's a transition between it being rocky and it being a mini ice giant or some other kind of composition. So it's not perfect. But really the problem with Kepler 452b is that it might not be there. The signal that we see in the Kepler data that looks like it might be Kepler 452b looks very similar to other sources of noise in the data. So it's very hard to disentangle whether this is a true signal of a true planet or if it's just instrumental noise in the data, because there's a lot of other instrumental noise in the data that looks just like this. So we think our best guess is that it's about 50-50. There's a 50% chance it's real and potentially a rocky planet around a sun-like star in the habitable zone. And there's a 50% chance that it's noise and it's not there at all. So don't get in your spacecraft right now and go because we don't know if it's there. So in terms of Earth twins, proper Earth-like planets, we haven't got a very good example yet, something that definitely looks Earth-size, habitable zone, sun-like star. So another planet that someone mentioned was Mongo. And yeah, we have not found Mongo or, Caprica or Beta Z or any of these truly Earth-like planets from science fiction. We have not found yet. We're still looking. That's like the quest, the Holy Grail. And we haven't, it's another artist impression. We haven't found any of these yet. That's Beta Z from Star Trek again. No Earth twins yet, but we're looking. What we did find was a whole bunch of really interesting stuff. And I just want to spend maybe another few minutes talking about some of the cool systems that we did find, if it doesn't crash again. Okay, so this is a pretty classic image. We're going to jump franchises again. This is Star Wars. So this is Luke on the surface of his home world, Tatooine. And it's orbiting a binary star. This is a very famous sunset of the two stars setting. Now, I mentioned earlier that we have found planets around binary stars. Kepler 47 was an example. The first one was actually Kepler 16. And that was just I think that's maybe the most press that Kepler ever got in the course of its 8 years, was when we found a Tatooine-like planet for the first time, because people could really understand that, right? Like, this is such an iconic image. And now we found about a dozen planets orbiting binary stars. This is another example. So this is, now I'm going to forget which is the system. I think this might be Kepler 16, actually. So this is the Kepler 16 binary system. So it's got a yellow star like our sun, and then an M dwarf companion. A lot of the times binary stars will have M dwarfs in them. And this is Kepler 16 in the foreground. And one of the things I like about this press image is George Lucas even got the colors right of the stars. Now, remember, like, Star Wars came out in, the early 70s. Like, this was 25 years before we'd found any planets, let alone real planets around binary stars like this. And he even got the colors right. Not the sizes, but, again, this was decades before we'd found anything. So my hat is off to him for coming up with this truly very imaginative system that we ended up finding an equivalent of, which was very cool. All right, I'm going to skip franchises again to the Marvel Cinematic Universe, MCU. This is, and I'm going to read this telephone number because, again, exoplanet names are atrocious. This is Ogle 2015 BLG 0051b. This is the farthest away planet that we've ever confirmed. There was actually some recent buzz a month or two ago about a potential extragalactic exoplanet where a team found an X-ray transit in another galaxy. They were looking at a source in X-rays, and it dimmed in kind of the way you expect a planet to dim something. It's too far away for us to confirm, but it's a really tantalizing signal. But in the meantime, the farthest away planet that we've ever confirmed is Ogle 2015 BLG 0051b, which is 26,500 light years away. And the interesting part is it's towards the galactic center. So we're about 30,000 light years away from the center of our Milky Way galaxy. So picture a spiral galaxy. There's the center. We're kind of out here in the burbs. So we found a planet that's 90% of the way to the galactic center, which is very, very cool. And this is, again, artist impression. The reason I brought this one up is it's kind of like Vormir. So Vormir, if you remember from the MCU, is where the Red Skull is holding the Soul Stone. And the reason they're similar is Vormir is described as like a planet at the center of celestial existence. So for us, that would be the center of our galaxy. And this is as close as we've gotten to the center of our galaxy, 90% of the way there. So Ogle 2015 BLG 0051b is the closest thing we have to Vormir from the Marvel Cinematic Universe. Okay. Oh, another request from the crowd was Arrakis from Dune. I hope you all got to see the movie. It was the first time my husband and I had gone to a theater in nearly 2 years, but it was worth it because it was, an incredible visual spectacle. I'm really glad I got to see it on the big screen. So Dune is, a rocky planet orbiting a red giant star. And we have actually found planets orbiting red giant stars. In the books, the red giant star in question is Canopus, and we have not found a planet orbiting Canopus yet, but we have found planets orbiting red giant stars. So our sun, in a few billion years, will run out of hydrogen and helium at the center of the star, and it'll start the next phase of its life. So one of the things it'll do is it'll start puffing up its outer layers, and that'll become a red giant. So the sun will expand to come out to close to Earth's orbit. So Mercury will get swallowed up, Venus will get swallowed up, and it's going to get really big. It's going to turn into a red giant. And we have found planets orbiting stars at this stage of life, which is really interesting, right? Because thinking about our solar system, we'd love to know what is the fate of the Earth going to be when the star turns into a red giant. After the star is a red giant and those outer layers have puffed all the way off and become, hopefully a beautiful planetary nebula, what will be left in the middle for the sun is something called a white dwarf. Now, this is just like a cooling hunk of carbon and oxygen, which will basically just like radiate away heat forever until the heat death of the universe. And this white dwarf, we call it, this hunk of carbon and oxygen, is kind of the final stage of evolution for our sun. we've also found planets orbiting white dwarfs. So it is possible for planets to survive this, massive evolutionary change of their host star and to still be there. Now, the planets that we found, we don't know yet whether they are original planets that survived this evolutionary phase, or if they're like second generation planets where, the first generation of planets got distorted and destroyed and flung about by this evolutionary phase change of the star, and then coalesced to form a new generation of planets. We don't know yet whether they're old or new, but that's something that's really exciting to think about, because again, thinking about the Earth, what will happen to the Earth in 5 billion years when the sun turns into a red giant? Now we have some evidence that planets can survive this, so that's good. Okay, one of the last few systems I wanted to talk about is Trappist I. So remember I mentioned M dwarfs, so very cool, very red stars. Trappist I, this host star here, this is another very cool graphic made by my colleagues, is about as small as a star can get and still be a star. It's 8% the mass of the sun. It's right on the limit of how small you could be and still like start burning hydrogen and helium at the center. And it has 7 rocky planets around it, 3 of which we think are in the habitable zone. One of the cool things about the system is that the planets are packed in super tightly. So the 7 planets have periods out to 30 or 40 days. So this is 7 planets that are closer to their star than Mercury is in our solar system. So you have to imagine our solar system and just like squeeze it all in really close to the star. Now, the way that stays dynamically stable is that these planets are in resonances with each other. So their periods, their orbital periods, are related to each other. Now, we see resonances in our solar system as well. So the Galilean moons around Jupiter, 3 of them are in a 1 to 2 to 4 resonance. So every, one time, for every one time Io goes around, the next one goes around half as long, and then the one out from that goes around a quarter as long. So every one time the outer one goes out, Io has gone around 4 times. It's 1 to 2 to 4. And so they're related to each other. And that means they stay locked in this resonance. So the 7 planets of Trappist I are locked in a series of resonances. And that's how you can have so many planets crammed in close together. I think this is the last system I want to talk about, and it's called K2138. Now, K2138 is another compact series of planets that have a set of resonances. The reason I love K2138 is because it was found by citizen scientists. It was found by people at home looking through Kepler data. So I was lucky enough to get to co-lead this large citizen science program for Kepler data. And we got to be on TV. It was very cool. And so they announced it on TV, and all the people watching TV immediately went to their computers and started looking through the data. And within 24 hours, we had found this new system of 6 planets in total. We know it has 6 planets now around a K star. So a K star is a bit smaller than the sun, but not small enough to be an M dwarf yet. And it's also in this series of resonances. Now, the interesting thing about the planets around K2138 is that they're all in 3 to 2 resonances. So for every 3 times the inner planet goes around, the next one goes around twice. For every 3 times that one goes around, the next one goes around twice, and so on. So the 5 planets, the 5 inner planets, are all in this chain of 3 to 2 resonances. The reason 3 to 2 resonances are cool, if you're a musical theorist, the 3 to 2 resonance is the perfect 5th interval in music. So the difference between the tonic and the 5th is a ratio of 3 to 2 in the frequencies. So those 2 notes have a frequency ratio of 3 to 2. So K2138 is playing music. So the very cool people at System Sounds went and made essentially a music video for this system found by citizen scientists. So I'm going to start playing it. Hopefully you'll hear it. I'll just let it play for a minute. Now, what's happening is every time a planet transits the star, the music plays a note, and the note is related to the frequency of that planet. So the planet that's in the middle zooming around has the highest note, and the planet that's furthest out, that's going slowly, has the lowest note. And the reason it sounds pretty is because it's this chain of resonances. It's like, if you put Twinkle Twinkle in a blender or something, this is the 3 to 2 chain of resonances. So this is just, we'll take a moment of Zen towards the end of the talk. So this was made by the folks at System Sounds, and I wanted to encourage you guys, especially, during the pandemic when everyone's kind of looking for online hobbies, go to planethunters.org, which is our citizen science project for TESS, which I'll talk about in just a second, and look for a planet. And maybe you can find the next K2138 or the next even more wild and wacky system that we haven't even imagined yet. I mean, one of my favorite things about being a planet hunter is getting to find things that we didn't even think about, right? Like, Tatooine we thought about, but there are these, these chains of resonances that are so unique and different and cool. I keep being surprised by what we find. So I'll finish by talking about the current NASA mission that's finding planets. It's called TESS, the Transiting Exoplanet Survey Satellite. So it launched in 2018 and it's doing an all sky survey. So remember I said Kepler looked at like that one patch of sky in the constellation Cygnus for 4 years. TESS is doing the whole sky. So far, it's found hundreds of planets around bright stars. The exciting thing about the planets that TESS finds, I won't start replaying this video because I don't want it to crash PowerPoint. The exciting things about the planets that TESS finds is they're around bright nearby stars. Those are the targets of TESS. Now, because they're bright and nearby, that means we can learn more about the planets. Most of the, few thousand planets that Kepler found, we don't really know much about. We know their period and we know their radius. We know how big it is, but we don't actually really know what they're made of. We don't really know anything about their atmospheres or their surfaces. We just have these bulk properties. But TESS is doing this all-sky survey of nearby bright planets. Those we'll be able to actually look at with other instruments in much more detail, including what will launch this month, the James Webb Space Telescope. So the James Webb Space Telescope will be looking at the planets found by TESS and actually peering into their atmospheres and asking, like, do the atmospheres have biosignatures? Like, is there evidence of life? Can we see any evidence of continents or oceans in the light curves from these planets? So TESS is really going to give us the planets that we, study for the next 100 years, which is super exciting. And again, I'm just really excited to see, what does the universe throw up for us? What haven't we found yet? So the road from 2,500 years ago, when Plato and Aristotle were like, well, is there more than one Earth? Now we know there's more than 4,500 planets around other worlds. None of them look like Earth yet, but we think that there are Earths out there. So the search continues. But in the meantime, we've found some very, very interesting stuff. And hopefully you feel like you got to learn about some of it today. Thank you very much.
Jessie Christiansen, thank you very much. That was a wonderful presentation.
Oh, I'm glad you enjoyed it. And now there's time for questions. So what do you want to know more about?
Well, and I was going to say, hey, everybody, turn on your microphones and jump into the conversation. Time for questions. Anybody?
Why are we so focused on Earth-like planets? I was talking to a friend of mine today who's an inorganic chemist by training, and he said that even small changes in the compositions and the pressures are going to result in maybe a different kind of chemistry that might lead to a life form unlike ours, but maybe very viable for these other planets. I think we got to broaden our search here.
Yeah, well, and so an example of that is phosphine in Venus last year, right? Like there was this whole discovery of phosphine in the upper decks of the atmosphere of Venus where the temperature is low enough for some kind of life. I would say that the short answer to your question is money. So we need to ask NASA to pay for us to do these things. So if we have we can say we know of one place that life evolved. That's the one place we know. Let us look for those kinds of places and we'll see if we find other life. Like that's at least a logic chain that like a congressman will buy, right? If we ask for $1 billion to look for a kind of life no one's ever seen before, then that's just not as safe a bet. So the short answer is like money and politics, but you're absolutely right. There are many, many other kinds of life you could potentially imagine. I mean, life is just, chemical energy gradients. Basically, how do you turn one form of energy into another? What's the chemical pathway? And people have come up with really imaginative ideas for other chemical pathways where you're turning energy from one form into another. So there's a lot of work that's being done on that. It's really hard to convince Congress to pay for something that's too speculative. So for instance, technosignatures. technosignatures are astrophysical evidence of intelligent civilizations out there. So you could search for things like radio or transits by shapes that are not natural, like a triangle or a spaceship or something. You could look for laser pulses coming from planets. You could look for things like Dyson spheres, where a planet has, surrounded its star with a shell to capture all of the energy from the star. So there are really cool ideas for how you could search for that kind of evidence of intelligent life, not biological. So you're not making any assumption that it needs water and it needs oxygen, but you're making some assumption about the kind of technology you would see. And those have had a really hard time getting funded. So there was actually like a 2-decade period where you were not allowed to ask for money to do something like that. Like it was actually forbidden in the budget. Thou shalt not do SETI, search for extraterrestrial intelligence. Just in the last 5 years, that's actually been walked back a bit. And there was actually like a $10 million line item for people to start investigating technosignatures in more detail. So I'm hoping that signals, a bit of a shift. And that would allow us to do more speculative searches. But in the meantime, people are trying to work through the biology and the chemistry to be like, what would another pathway be that we could look for where we'd know that if you saw it, it's not geophysical or geochemical, like it has to be biological.
Not many like that.
I know the fellow who was Clinton's energy secretary quite well. And I once asked him how easy it would be to sneak, let's say, $10 million through the budget. And he said to me, Mike, he said, no chance. He said, there are people that go over it with a fine-tooth comb. You can't sneak $1 million through it.
Yeah, I guess that's a good thing so that people can't do that. But it is frustrating that, if you think about the entire budget of like the Pentagon or something, and you're like, I just want $10 million. It's chump change. You lose that in the couch.
Yeah, that's true.
Jessie, you mentioned that the planets, the exoplanets you found so far tend to be bigger. And do you think that's because of technical constraints or because in fact they're just bigger?
So we're speculating a little, but we think that they're actually more common, given the spaces where we can find rocky planets, where we tend to find these super Earths instead of rocky planets. So there is parameter space where we are sensitive to rocky planets. So for instance, very close to the star. And that's basically because the transits happen much more often. So you can just add up the signal to noise. You just watch it over and over again. And you end up, if you have 100 transits of a shallow planet, you'll get a good signal to noise. So there are places where we're sensitive to rocky planets. And when we look in those places, we still more often see these super Earths and sub-Neptunes. So we think that they're actually genuinely more common than rocky planets. But we are kind of extrapolating a little bit especially out at distances like the Earth from the sun. There we're really not constrained by the data, is how I'll say it generously.
Other questions?
Okay, I'll ask it.
Yeah, go ahead.
Okay, I would expect that since baryonic matter heavier than lithium is produced through stellar genesis, that the earliest stars would not have planets. And as we go to succeeding generations of stars, you'll get more and more planets because there's more material to form them from. Is there any hope that we could ever extend our knowledge to some of these other census of exoplanets?
Yeah, so those are really good thoughts. We think that the very first generations of stars, the only kinds of planets they could have had around them are gas giants made out of mostly hydrogen, helium, that were born from like gravitational turbulence. So there was a disk of mostly gas, because there's not a lot of dust yet, a disk of gas, and there's some kind of interruption, and you get a bit of turbulence and you get a gravitational instability and it collapses. So the only kinds of planets we think could have formed around like the first and second generation of stars are these gas giants that are born from gravitational instabilities, as compared to nucleated cores of dust like planetesimals that grow and accumulate, because those are the ones where you need the planetesimals, you need the dust, you need the remnants of stars. So that's kind of so stellar age, so how planets form as a function of stellar age, is an open question of research right now, and it's actually something I'm really interested in. So one of the things we're trying to do is map out occurrence rate as a function of stellar age, like the very earliest stars, how many planets do they have around them and how often do you see them versus like the younger stars that we see today, how often do they have planets around them? So that's something we're trying to research right now. It's hard because stellar ages are not well known. That's actually hard to measure. Basically, once a star gets on the main sequence, so basically, as soon as it's like a proper, well-formed star that's just burning hydrogen, helium, a lot of stars don't change much for the next 5 billion years. And it's like, how old are you? So unless it's like pretty early on, or if once it's getting to its evolved state, there's a lot of uncertainty in there. So we're thinking about it really hard. We haven't made a lot of progress yet, but your intuition is correct.
Other questions? Hey, could I follow up on the discussion about money and budgets and finances? Just to look out into the, suppose you had $10 billion to spend over the next 10 years.
Mm-hmm.
And you could allocate that as you saw fit. What programs or what technologies would you put that money toward?
Sure. So I'd probably take $1 billion of that to put a very high resolution spectrograph in space. So one of the very cool things that has happened recently on Earth, on the surface, on the ground, is that we've been able to use high resolution spectrograph to look at the atmospheres of exoplanets in a lot of detail. So when you have very high resolution, you can start to look for individual atomic lines, and then you can tell, like, you know, is it in its excited state? What temperature is it? And you can start to measure things like wind speed, like how fast is the wind moving on this planet? There's a lot of things that you can do if you have enough resolution. Now, being on the ground, though, is a pain because of the atmosphere and the sun comes up every day, which we all get annoyed by. So if you go to space, you have a lot less noise and a lot less sun. So I would take $1 billion and put $1 billion and put a high resolution spectrograph in space, just so that right now we could do some cool stuff with atmospheres. Thinking about the future, I would take the other $9 billion, and there's 2 technologies that I would work on. One is directly imaging exoplanets. So for instance, at Palomar on the Hale telescope, we have FARO, which is the adaptive optics system, where what you're doing is basically you're beating the atmosphere. The atmosphere is blurring out your stars and blurring out all the light. And we use adaptive optics to correct for it on the fly. And you're basically trying to cancel out the noise from it's like a bunch of spinning plates. You're trying to cancel out the noise from the atmosphere so you can just see the star. So this is one of the things I do with Palomar, is look at stars that host planets to see more about the star. If you have a good enough instrument, you can actually see the planets next to the stars. So things like, you know, on the Gemini telescopes and on the Keck telescopes, they have these very exquisite direct imaging instruments where you can actually resolve a planet going around a star. You can separate them on the sky. That only works at the moment for very young planets because they're very hot. So Jupiter, when it was like very first forming, is a contracting ball of gas, radiating out a lot of heat. So it really only works for young giant planets so far. What would be the most amazing thing in the world would be an actual image of an Earth-like planet, right? Like you'd actually see it. You'd actually be able to get the light and get a spectrum, rather than all of these other techniques, which usually involve getting a spectrum of the sun or the star and subtracting out the noise and trying to see if you can see the planet. This would be directly getting a spectrum of the planet's light. So that technology needs a lot of improvement to get from hot, young, giant planets to cool, rocky, small things. There's like several orders of magnitude of improvement that are needed. So I put a bunch of money there. The other place where I'd put the other half of that future technology development is in star shades. So a star shade is basically you have a telescope in space, and then formation flying, you have another spacecraft essentially far away from it that you're using to block the light from the star so that you can see the planet. So if you imagine this is the planet. So I'm going to have another spacecraft basically in front of my telescope, like tens of thousands of kilometers away in space, to block the light so I can see the planet in more detail. This is super cool and has been shown in simulations to do like really cool stuff. Like you can really bring out the planets in more detail, but it hasn't been tested yet. So that's where I would spend the other half of my future technology money.
Wise choices, very good choices.
We just have to get you into Congress.
Yeah. Just I'm actually not American, so they wouldn't let me. Sorry.
Other question? Anybody, please jump in. Please jump in.
Okay, a silly question.
I
Doctor Who
won't go there.
had a robot dog.
K9. Yep.
Yeah, K9. And, there was two versions of him, as it turned out. He left one behind with one of his companions.
Sarah Jane.
Sarah Jane. Why not a cat?
I guess the writers were dog people.
Yeah, maybe.
Makes me sad. I'm a cat person, as evidenced by everybody who was on the call at the start. I had to extricate 2 kittens from the room so that I could actually give this talk unmolested by claws and chewing on the headphones and stuff.
From the sublime to the ridiculous.
Yes.
We've talked about Kepler, and we've talked about TESS. How will the Nancy Grace Roman telescope extend these surveys?
Right. So there's two real areas of exoplanet science that Roman will really push forward. One is, so Roman will have like a mini version of what I talked to you about, which is a coronagraph. So the coronagraph has the blocker, but the blocker's in the instrument. It's not like formation flying tens of thousands of kilometers away. They actually just put a piece of hardware in front of the CCD. It's very, I say it like it's like, I don't know, a block of metal or something. It's a very sophisticated block that they put in. So this will be one of the first times there'll be like a coronagraph in space that's been designed to do this. And it's not going to be good enough for the Earth-like exoplanets. It's going to be, for the hot young giants. But it'll be it's called a technology demonstration. So we're going to prove that we can do coronagraphs in space. That's what we'll do with Roman, and that'll really lay the groundwork for future missions. The other thing that Roman will do. So remember, I mentioned that Kepler's job was trying to find out how common Earth-like planets were. So Kepler really investigated the inner solar systems around stars. So that would be in our solar system, the equivalent of like the sun out to Earth. But we haven't done a good survey of the outer solar systems of planets yet. And that's what Roman will do. Roman is going to do an outer solar system census around other stars. So we can actually start to say like, okay, we know rocky planets close to the stars are common. What about rocky planets further out and giant planets further out? How common are they? So Roman will really complete the census that Kepler started of the populations of planets around stars.
Well, I mean, you mentioned that super Earths are most common, but isn't it true that our detection methods introduce a bias into this? I mean, you talk about planets further out, how do we, using the methods we're using, how do we detect a planet 12 astronomical units?
It's a great question. So in part because it's a technique I haven't talked about yet. So Roman uses a technique called microlensing. So microlensing is when so the basic premise is, go back to Einstein, everything that has mass bends space-time. Like you're bending space-time around you right now because you have mass. So what happens is we look towards the center of the galaxy. We've got 100 billion stars in the center of the galaxy. So they're like a background screen of lights, essentially. Between us and that screen is the rest of the galaxy. And so planets and stars go between us and the background stars. And what they do, as those planets and stars are moving through the galaxy, they're bending space-time around them. It's like basically if you took a magnifying glass and ran it across the center of the galaxy. Now, what we do is we monitor the brightness of all of those stars in the center of the galaxy. And instead of seeing a transit, which is what you see if the planet is close to the star and blocks the light, what you see is a magnification. The star in the background gets really bright and then gets fainter again. And that's because the planet and the star in the foreground between us and the center of the galaxy are bending the light. So it's bending more of the background light towards us. So it's relativity, it's complicated, but basically what you do is you're looking at the background stars for them getting magnified by these lenses in between, microlensing. And then the very specific shape of the brightening, that magnification tells you whether it's a star or a planet or a star and a planet or two stars and a planet, et cetera, et cetera. So that's And that's where that is most sensitive is actually between 1 and 10 AU, just given the scale of our distance to the center of the galaxy and where stars and planets are most likely to be in between us and there. The peak sensitivity is for planets and stars that are separated by 1 to 10 AU. So that's that next part out of our solar system.
Wouldn't that require, that microlensing technique, wouldn't that require a tremendous increase in sensitivity of our instruments and all? I mean, we're looking at very small effects today.
Actually, so microlensing is a much larger effect than the transit. So the stars actually get multiple magnitudes brighter. Like their brightness increases by up to an order of magnitude. So, you know, they actually get quite significantly brighter in these microlensing events. The problem is they happen incredibly rarely. So what you need to improve is the footprint on the sky. So Roman has this big field of view, much, much larger than Hubble, and it's just going to stare at the center of the galaxy, waiting for these brightening events. Because they're very, very rare. But if you look at a billion stars, then even a rare event happens pretty regularly. So the actual change in flux from these stars is quite high. So a transit of an Earth-like planet blocks 85 parts per million of the light. So like 1% of 1% of the light gets blocked by the star. So you're looking at incredibly tiny changes. But a microlensing event increases the flux from the star by 10. It gets 10 times brighter as kind of there's a spread, but that's an average. It gets 10 times brighter. So it's easy to see. The telescopes on the ground, little telescopes on the ground can see it. And there's a whole ground-based network around the world that follows up events. So they take a while. So a transit, it takes Earth 6.5 hours to transit in front of the sun. Microlensing events can take days or weeks because, you know, everything feels like it's moving very fast, but the scale is so big that it's not actually that fast. So what happens is we have these ground-based systems that are looking for the starts of these magnifications, and then alerts go out to this ground-based network of like amateur astronomers with telescopes all over the world. Like, okay, this star's brightening, everybody go look. So you see these like characteristic light curves where it's like you see the few dots at the point, and then a whole bunch of data appear as everyone's like, this one's magnifying. And then you watch it go up and then come down, and then you start to fit models to it and say like, okay, does this one have a planet or not? Sorry, that was probably more detail than you needed.
No, but I was wondering how that was happening.
Yeah.
That's fascinating. I mean, are they picking up some of this data from ZTF?
Yeah, so I don't know if ZTF specifically alerts on microlensing events. The two big ground-based networks are OGLE and MOA. Oh, there's three now, KMT, the Korean microlensing telescope. So those are the three telescopes that are searching every night and then alerting. ZTF is doing more like supernovae and gamma ray bursts and counterparts of GRB, of gravitational waves and stuff.
Had to get back to Palomar.
Yeah, I have to get ZTF in there somehow.
Had to get that in there. Well,
I have a question.
Yes.
If we have a little more time.
Yeah.
I'm just getting in, I'm a photometrist. I'm just getting into I've been admitted to the TESS follow-up program.
Fantastic,
and,
thank you.
So I'm just beginning to submit data on transits to the program. And I'm wondering, how long is this program going to be useful? Is the amateur participation going to be useful to this program? Is it going to be
yeah, so that's a really good question. So right now, TESS is in its first extended mission. So in the prime mission, so like 2018, 2019, start of 2020, we did most of the southern sky and like 2/3 of the northern sky once. We looked at each field once. In the first extended mission, which is what we're doing right now, we're finishing the northern sky and doing the ecliptic plane, which we had missed the first time. So there's still a lot of new discoveries coming out that are short period planets around these bright stars that all need follow-up. What's going to happen in the second extended mission is we're going to start going back to those fields. We've started some of the south, but we're going to keep going back to the fields, and then we'll be finding the longer period planets. So when you're looking for a transit, if you only see one transit, it doesn't give you enough information. Because for instance, in our solar system, Venus and Earth are the same size, but they're very different planets. So if you saw one transit, you don't really know what you've looked at yet. you really want to see 3 transits. So you know that you know the period well. So as Tess goes back in the second extended mission and is looking at these fields again, there'll be more and more long period planets that we still need help with. So there'll be more targets that we find planets around. So the second extended mission will be like 2022 to 2024. So at least until 2024, there'll be new stuff coming out. And that's just, you know, the basic stuff that we ask people to do right now. Once there's all of this whole library of planets, the next thing we need is transit timing variations. So if you have a single planet going around a single star, it's a 2-body problem, it's solved. The orbit is exactly Keplerian and exactly periodic. As soon as you have more bodies in that system, like even in our solar system, Earth's orbit isn't exactly periodic because it's getting pulled on by Jupiter and Saturn and Mars and Venus. And it actually creates a measurable delay in when you see Earth's transit. So if you were an alien civilization looking at the Earth, you wouldn't see Earth come back exactly 365.25 days. Sometimes it's a bit early and sometimes it's a bit late, depending on Jupiter and Saturn. And this is one of the ways, A, that we measure the masses of planets is by measuring these transit timing variations, and B, how we find like hidden planets in those systems. Because if you only see one planet, but it's arriving early and late, you know that there's something else in that system that's inducing these variations. So after we do all the obvious stuff, which is like all of the low-hanging fruit of these planets, there's a lot of follow-up work to do to like measure the times of transits of all of these and be like, let's find more planets and let's make sure we understand these planets really well. There'll be work forever. There'll be work forever is the short answer.
So it's good to know that we have job security in this area. Yeah.
Yeah, I don't think you're getting paid. But we, you know, Tess's success depends on this network of ground-based volunteers. Like, honestly, it really does. So, you know, I'm on the Tess follow-up committee, Tess follow-up working group steering committee. So, you know, SG1 and is one of our subgroups. And, you know, one of my delights in life is adding volunteers to our papers as co-authors, right? Every paper we get to add a few volunteers for people who've contributed data. You guys are doing the work, you get on the papers. It's very cool. So thank you so much, like for volunteering your time and your data, because that's what's making Tess a success, is this ground-based network.
Well, you're welcome. It's very rewarding work.
Yay.
And please tell us again, what's the website?
So for citizen scientists, so that's just people looking through the data, it's planethunters.org. For what John is talking about, if you have a telescope that has a CCD on it and you can take photometry, then you can join the Tess follow-up working group. I don't know what the website is off the top of my head, but if you Google Tess follow-up working group, you'll find it.
Very good.
And yeah, it's fantastic to have people. We need this. There's thousands and thousands of candidates that we need help clearing. So any help is appreciated.
We'll get right on it. Dr. Jessie Christiansen.
Thank you so much for having me. My next time at Palomar is like in 5 weeks. So I'm really hoping I can actually get there. That would be great.
Oh, please. I hope.
Yeah. I have two nights on the Hale telescope.
Well, and you've been very gracious with your time. And well, we're running almost toward an hour and a half here. So
no worries. If anybody thinks of any more questions, just email me, get in touch.
But thank you very much.
Thank you.
Thank you.
I think.
Thank you. Great talk.
Outstanding presentation. Thank you so much.
You're very kind. Thank you.
With that, we'll shut the meeting down now, but let me quickly make a note on our next meeting. The Greenway Talks online will continue on Saturday, December 18th, when our guest will be J. Kelly Beatty, senior editor, now retired, at Sky and Telescope magazine. Kelly's going to have some photos and show us what it was like at Sky and Telescope for almost 5 decades. But this presentation will be done as a discussion and interview. So it'd be a little bit different format. And by the way, 12 hours ago, Kelly was on a cruise ship bobbing around the Drake Passage, hoping for a break in the clouds. I don't know if he was able to see the eclipse or not, but he will show us some pictures and tell us all about it in 2 weeks. So again, thank you to Dr. Christiansen, and thank you to all of you for joining, for being here, for supporting the Greenway Talks. And with that, I'll close the meeting.
Thank you.
Everybody. Everybody wave. Bye-bye.